morning, everyone. So today we're going to solve problems where we're going to see applications to Newton's Newton's laws of motion in general, and more specifically Newton's second law. And we're going to focus on circular motion. So let's start with first problem. Consider a conical pendulum with an 80 kilogram bulb on a 10 meters wire, making an angle of 5 degrees with a vertical, as you can see in this figure in here. So the angle, this is the angle theta, which is equal to 5 degrees. This is the bulb, which is attached to wire, and they are attached to the ceiling. Now you have to determine in part A, the horizontal and the vertical components of the force exerted by the wire on the pendulum, and in part B, the radial acceleration of the bulb. So let's start with the first part. So if we're going to solve this problem, and we are required to determine the components of the force exerted by the wire on the pendulum, then we would need to apply Newton's second law, because it's the only Newton's law which gives access to the forces. This is why let's take the bulb as our object, and let's draw all the forces which are exerted on this bulb. So first of all, we have the gravitational force, which is the force exerted by the Earth on the bulb, and then you have the tension, which is the force exerted by the wire on the bulb. Those are the two forces exerted on the bulb, and now all we can do is to apply Newton's second law. However, before to go there, let's just draw here this vertical direction, so the vertical axis, which is parallel to the to that one. And you recognize that the angle between the tension T and this vertical axis is the same. It is theta. So if we take actually two directions, so let's say this is the y direction. Let's take just an x y coordinate system, and we take this to be our x-axis. So x and y, they are again the same as we have taken them in previous exercises. So they are just the horizontal and the vertical axis. Actually, we can recognize immediately that we can access Tx and Ty. So we are required to get the horizontal and the vertical components of the force exerted by the wire on the pendulum. So we need to determine what are Tx and Ty. Now, you can see immediately that here, the projection of the force T onto the y-axis, this is nothing else than T cosine theta. And the projection of the tension T onto the x-axis is nothing else than T sine theta. So this is T sine theta. Right, this one. Now, theta is known, it's equal to 5 degrees. However, T, the tension T, is not known. So if we get the value of T, the tension, then Tx and Ty could be easily determined or evaluated. So let's see, can we get the value of T? Actually, we can do it. So let's just apply Newton's second law on this bulb. So sum of external forces is equal to, or F net is equal to the mass of the bulb multiplied by its acceleration. Now, the bulb is moving on a circle, on a horizontal circle. So it's moving in this plane, in this horizontal plane. It's not moving upward or downward. We are sure about it. So let's write T plus mg equals ma. And let's make the projection of this equation onto the y-axis. So if we make the projection onto the y-axis, we'll end up with plus T cosine theta minus mg. So I'm just making the projection of these forces along the y-axis equals 0, because there is no motion along the y-axis. The bulb is moving in the horizontal plane along a circle, and it's not moving up or down. So therefore, we can immediately deduce that the magnitude of the force T, it's given by m times g divided by cosine theta. So m, g, and theta are known, and so we can get the value of the tension. Once we get the value of the tension, so this this is t, then we can immediately deduce. So ty would be equal to t times cosine theta, and tx will be equals to t times sine theta. And this way we are done. So just have a look at the results. We end up with t equals 787 Newton. And just by applying, sine and cosine for the y and the x, for the x and the y components respectively, we end up with these components of the tension. So that's it for the first part. Now let's move to the second part. We need to determine the radial acceleration of the bulb. To determine the radial acceleration of the bulb, we need to actually apply Newton's second law on the radial direction. So it seems that here the radial direction is the same as the x direction, because the x direction is the direction that goes inward. So it goes into the center of the circle. So it's nothing else than the centripetal acceleration, centripetal direction, and the acceleration along the x-axis is nothing else than the centripetal acceleration. So let's actually apply again Newton's second law, which is this one, and let's project it onto the x-axis. So let's go on. Onto the x-axis, we end up with, so the tension T in this case does have only one component along the x-axis, which is plus T sine theta. So we end up with T sine theta. mg doesn't have any projection onto the x-axis because it's perpendicular to it. So we end up with T sine theta equals to m times AC, where AC is the centripetal acceleration, which is along the x-axis, as you can see in here. So this is the centripetal acceleration, which we know about. Because the bulb is moving on this circle, right? So look, have a look. The bulb is moving along this circle, and at any point along the circular path, the bulb has always a centripetal acceleration, which is pointing towards the center of the circle inward. So this is AC. So if you take the bulb at this position, so where it is on the right-hand side of the circular path, then this would be its centripetal acceleration. It's connected to the wire. It's just the wire connected to the ceiling, and then this AC is just along the x-axis, which we have taken to be pointing leftward. So we end up with T sine theta equals to MAC. And so from here we can deduce that the centripetal acceleration as a magnitude is given by T times sine theta divided by M. We just do a numerical application, or simply Tx, because we have Tx. So this is nothing else than Tx over M. We know what is the magnitude of Tx. We know what is the value of the mass. We just have to make the numerical application. And we end up with AC equals 0.85 meter per second squared. So this is the way we solve such problem. We had used the Newton's second law to access both the forces, the magnitude of the force, which we require to evaluate, which is the tension in this case, and to access as well the acceleration, and in particular the radial acceleration of the bulb. So that's it for this problem.